Hi everyone and welcome to a new video about noise analysis in op-amp circuits, and this is our example number 4. In this example we will look at a non-inverting amplifier with a cascaded RC low-pass filter. So we have a low-pass filter in cascade with a non-inverting amplifier. As before, we will look at our calculations step by step and also verify these calculations using SPICE simulations. So let's look at our example. What we have for this case. We have the given circuit here with the R1 is 1 kilo ohms, R2 is 19 kilo ohms, and we have the R and the C, which is then the external cascaded RC low pass filter. R is 4 kilo ohms and C is 1 nanovarads. And we have the op-amp OPA 209. Now we would like to calculate two parameters, two values, which is the input deferred RMS noise voltage and the output deferred RMS noise voltage. So let's look at our solutions. How do we do this? Now before we move on, it is important to also discuss the op-amp specifications briefly. Now from the datasheet of the op-amp OPA 209, you will have these two noise spectral densities plot. So the left side is the input noise voltage spectral density, and the right side is the input noise current spectral density. So we will use this later on in our calculations. What you also see in the datasheet of this op-amp are the parameters like the open loop gain and also the frequency response and some specific noise values at some conditions. So let's summarize what we need from this datasheet. We need the open loop gain, which is 132 dBs. That is actually shown here. We also see from this very important parameter the gain bandwidth product, GBW, which is then 18 megahertz, which is shown here. So the gain bandwidth product. What we also have is in the noise spec the broadband noise voltage spectral density, which is given by this symbol. It is 2.20 nanovolts per root hertz, and that is actually shown here with this unit. So you can see it is noise density, specifically then for the input noise voltage. We also have that actually in the graph, which is shown here on the left side, we see that it's 2.2 nanovolts per root hertz, and that will stay constant, and that is actually why we call it a broadband. We also have a similar part for the noise current spectral density, which is then in this case 500 femtoamps per root hertz, and that is shown here, and we also have these units. Again, this can be seen from the plot of the noise current spectral density at the input. You can see that this is the constant value and has a value of 0.5 picoamps per root hertz, which is then exactly equal to 500 femtoamps per root hertz. In addition, we have the region which is frequency dependent, and also here for the noise current spectral density. So for 1 over f noise voltage spectral density at some specific frequency 0.1 hertz, you can see that it is 20 nanovolts per root hertz. That's actually shown here. So at this frequency 0.1 hertz, you have a value of 20 nanovolts per root hertz, and that will be required later on in our calculations. In a similar form, we have the 1 over f noise current spectral density at the same frequency given by this symbol, and that is 3.75 picoamps per root hertz, and that is shown here again at the same frequency. So that are the op-amp specifications we need in the further calculations for these two parameters. So let's move on to the next step, and we will look in the next step to the circuit performance. So what we get from our circuit. So we have the gain, actually the gains. We have two gains. We have the signal gain, close-up signal gain, and we have the noise gain. So this is a non-inverting amplifier. We have the input voltage at the non-inverting input, and we have the feedback configuration with the op-amp and also our low-pass filter in cascade. Now looking at only DC part, then the signal gain is just the very familiar formula for the non-inverting amplifier, which is then 1 plus the feedback resistance divided by the resistance seen at this inverting node to ground, which is then this formula. Now if you substitute the values, you will have 20. The next is the noise gain. Now, since it's a non-inverting amplifier, we also have exactly the same value for our noise gain, because the noise gain is by definition determined from the noise source which is placed in the non-inverting input of the op-amp, and then again using the same formula for the gain. And that is exactly the same, 1 plus the R2 over R1, and that will also be 20. So we'll have the signal gain is 20, noise gain is 20. So that's actually the same for this case. Now we also have the bandwidth, the frequency response of the circuit. We have the signal bandwidth and we have the noise bandwidth, which are really important. Now in this case we have also the external low pass filter, so that will also be very important to determine the actual signal bandwidth and also the noise bandwidth. If you just look at the datasheet of the op-amp and then just ignore this part of your circuit, of course we cannot ignore it, but just for the first step, then we can use this formula: signal bandwidth is equal to gain bandwidth product over the noise gain. So if you do the math, just substitute the values from the datasheet and also the noise gain, you will have 900 kilohertz. That will be the case when you don't have this external low pass filter. But we have an op-amp and it is in cascade with the RC low pass filter. Now we need to be very careful. We need to calculate the pole frequency P1 associated with the external RC filter, which is then given by this R and C. Now that's a very familiar and very straightforward formula. P1 is then equal to 1 over 2 pi RC. Now if you calculate this, just substitute the value for R, which is 4000, and for the capacitor is 1 nanovarads. I will have approximately 40 kilohertz, and a little bit accurate is 39.79 kilohertz. This is a very important result because the pole frequency P2, which is then caused by the gain bandwidth product and also the op-amp and the noise gain, was calculated here, and I just repeat it here just to give you another pole frequency. That was 900 kilohertz. But our pole frequency due to that external low pass filter is almost 40 kilohertz. So 40 kilohertz is much smaller than the P2, which is just determined by the gain bandwidth product of the op-amp and the noise gain. So if the P2 is large or P1 is much smaller than P2, the actual signal gain will be limited by the pole frequency P1, which is then the external RC low pass filter. So in this case we have that. So we have the pole frequency P1 is much smaller than the P2. Then the approximation can be that this will be limited. So the cutoff frequency or the bandwidth of this complete circuit will be determined by this external RC circuit. So the closed loop bandwidth is determined by the external RC low pass filter. Then we can assume that this is still a first order system, which is just determined by the dynamics of this RC. So for the conversion, of course, from the signal bandwidth to the noise bandwidth, if we haven't done that yet, we need the conversion factor for a first order system, which is then given by this pi over 2. So the closed loop noise bandwidth, the noise bandwidth then, is then given by the conversion factor times the P1, which is then our actual signal gain. Now if you do the math here, pi over 2 times that approximately 40 kilohertz, you will get 62.5 kilohertz. That is the noise bandwidth we'll use for our analysis. And this is a really important point here. Don't use this 900 kilohertz because that is really the case when you don't have that external RC low pass filter. So let's also look at the total noise voltages, because we have the input referred RMS noise voltage and we have of course the output referred RMS noise voltage, and those are related by this expression, which is just the output referred RMS noise voltage is equal to the noise gain times the input referred RMS noise voltage. So the input referred RMS noise voltage then is on its own again composed of 3 parts. That can be seen easily if you look at this model, because the op-amp now is here, of course, has some noise, but now is it noiseless, and we have added two noise sources, which is then an input noise current of the op amp and also the input noise voltage of the op amp. And of course we have the resistors and also the low pass filter at the end. So the input referred RMS noise voltage in total will be, due to the internal op amp noise voltage source, this one, and that will of course produce some input referred RMS noise voltage. We have also the input referred RMS noise voltage due to the internal op amp noise current, which is actually this one. So this is actually inside op amp. We just take it out and make a model of it. So that will be also the case. We also need to calculate that. And we have the input referred RMS noise voltage due to the resistors. So actually the resistor around it. And those are of course the thermal noises. So that will be given by this. And we need them both, all of them, all three, and that will be used to calculate the total input referred RMS noise voltage. And that is calculated using the root sum of squares. And that is given by this expression. So we have the first part, the second part, and the third part. And that will be, each of them will be squared, added, and then take the square root of that one. That will give you the effective input referred RMS noise voltage. So we'll now look at each part here to determine what the value of that is. So let's then look at the first one, which is the input referred RMS noise voltage due to the internal op amp noise voltage sources, which is then of course just looking at this one. So this value on its own is also composed of two parts, and we have seen the plot from the datasheet that it has a frequency dependent part and also a frequency independent part. So that frequency independent part is called the broadband or the white noise voltage part, which is given by this symbol, and we have the part which is frequency dependent, which is then given by 1/f noise voltage. So these two elements are both in RMS values, and we need to calculate them separately and then add them up to get the input referred RMS noise voltage due to the internal op amp noise voltage sources. So that will be again used or calculated using the root sum of squares. So that's actually the formula again, and we need these two elements. So let's then calculate each of them. So the broadband noise voltage is then given by an RMS value by the broadband noise voltage spectral density times the square root of the noise bandwidth. And the noise bandwidth was already calculated using that pole frequency of the external low pass filter, and it was 62.5 kilohertz. Now if you do the math here, you just substitute the values from the datasheet. This was 2.20 nanovolts per root hertz, and this is the noise bandwidth. I will get very close to 550 nanovolts RMS. The 1/f noise voltage in RMS value is given by this formula, and we have here several parameters, which is the FH is the closed loop noise bandwidth. The FL is a selected frequency that will also calculate your normalized 1/f noise source, which is then given by this E sub F norm. And for that we will also use the datasheet, because most of the time we will take for the FL 0.1 Hertz, and that will be then used to determine the value for that from the datasheet. So from the datasheet, I already placed it also here. You can see 1/f noise voltage spectral density at 0.1 Hertz is 20 nanovolts per root hertz. That's actually what we have. So that we have the following. The normalized noise voltage is then given by this value. So we have then this, which is then just from the datasheet, 20 nanovolts per root hertz at that frequency, so 0.1 hertz, and I will do the math, you will get this value, so 6.325 nanovolts RMS. Now I will substitute in here this value, and also for FH, which is then noise bandwidth, which is then 62.5 kilohertz, and also for the F sub L, 0.1 hertz. So if you do the math, you will get 23.10 nanovolts per root hertz. So we have both the broadband noise voltage and also the 1/f noise voltage. So what you then have in total, of course, in effective form, you will just use this formula. So using the RMS values of the broadband noise voltage and also the 1 over F noise voltage, you will have then this value. And you can see that the actual result is then a little bit larger than that 550, so it is 551 nanovolts per volts RMS, but you can see this part is not really contributing much. So the actual dominating term here is the broadband noise voltage, because the end result is very close to the separate part, which is just the broadband noise voltage. So we have now the first part of the input referred RMS noise voltage. So let's now move to the input referred RMS noise voltage due to the internal op-amp noise current, which is given by this E sub Ni. So that can be calculated using the equivalent resistance and also the noise current source of the op-amp. What is the equivalent resistance? Equivalent resistance is the resistance seen by the noise current of the op-amp. So this source will see a resistance effectively, and that is then determined and used calculate the E sub Ni, and E sub Ni is then calculated using Ohm's law, just current times resistance. So but EIN on its own is also composed of two parts, as we have also for the noise voltage. It is composed of the broadband noise current and also the 1 over F noise current. And that is also again calculated using the root sum of squares, using this formula. So very similar to the noise voltage analysis. So the broadband noise current, that's again RMS value of that one will be then the noise current spectral density times the square root of that noise bandwidth. So we already calculated noise bandwidth using the pole frequency of the external RC circuit, and we have this, and it will be 125 picoamps RMS. Now if you do also the part for the 1 over F noise current RMS value, and a very similar formula will be used, and we have then again the upper cutoff frequency, which is the noise bandwidth. We have the FL selective frequency, and it will also determine your 1 over F noise current, and this will be again taken as 0.1 Hertz, but any other value will do, and you will of course need your datasheet for that one. Now from the datasheet we can see here 1 over F noise current density at 0.1, and this symbol is 3.75 picoamps per root hertz. So if you now just add them up, substitute the values here and also the square root of 0.1 Hertz, that will result in 1.186 picoamps RMS. And I will now substitute this value in here, and also for the noise bandwidth in here, and 0.1 Hertz here. So if I now do that, I will have this expression that will give me 4.332 picoamps RMS. So I have now the necessary elements for my total noise current source of the op-amp. So what do I get is the following. Using then these two values and then do the calculation using root sum of squares, I have then the following value, which is then 125.1 picoamps RMS. So you can already see in this case also that the broadband noise current is dominating, because this part is not really contributing much, because this is also very close to that one. So again, the broadband noise part will dominate. Now the equivalent resistance must be calculated, and that is looking from the noise current source of the op-amp. R1 and R2 are in parallel. Why? Because this is of course disabled using superposition, and it is also disabled, so this is short, so for superposition these are all gone. And I have actually, looking from the current source here, this R1 goes to ground, and this will be also go to ground, because I will just disable this part. So I have the R1 and R2 in parallel. So that will be then, if you do the math here, that will be then exactly 950 ohms. Now I will use Ohm's law and then do the I sub n times the equivalent resistance. That will give me 119 nanovolts RMS. And this is very close to that value. So we have now the second part. So for the input referred RMS noise voltage due to the resistors, that are the thermal noise voltages, we can then calculate that using the formula for terminal noise voltage. And then, of course, use the equivalent resistance of the R1 and R2. So the equivalent resistance seen at the input nodes of the op-amp, that will be, of course, calculated, and this is the exact same result as before. And we will then have the following formula for that one. And this is then for KT R, which is then, of course, resistance seen at a node, and this is then a noise bandwidth. So we have the K, which is the Boltzmann constant, which is given by this value, the temperature, the absolute value of that one, and say at room temperatures, 27 degrees, which is of course a little bit hot. And then we have a round value using the Kelvin, so we have then T is equal to 300 kelvins. The R is the equivalent resistance in ohms seen at a node, and the noise bandwidth is the the noise bandwidth is then given in hertz. So for this circuit, we have then R is equal to 950 ohms, and our noise bandwidth will be 62.5 kilohertz. Then we have, if you just substitute in here the required values, you will have this, and I will have a 992 nanovolts RMS. That is what we have for the terminal noise voltage. So the total input referred RMS noise voltage then will be again calculated using the root sum of squares, but this is the formula as a repetition, and this is what we had for the input referred RMS noise voltage due to the noise current source of the op-amp only. The second part was then the input referred RMS noise voltage due to the noise current source of the op-amp only, and this is the part where we only consider the terminal noise voltage of the resistors. Now if you combine them together to have the, of course, the total input referred RMS noise voltage, you will use this formula, substitute values, and you will have 1.14, in this case, microvolt RMS. That's what we have now. Of course, we have now the input. Now we can move easily to the output referred RMS noise voltage using the noise gain, which is 20, and also, of course, the input referred RMS noise voltage. We just calculated that. So that will be then using the formula. Output referred RMS noise voltage will be the noise gain times the input referred RMS noise voltage. Now, if you do the math here, 20 times that value, you will have 22.8 microvolts RMS. So that is our results for our output referred RMS noise voltage and also the input. Now, in addition, we also look at the signal to noise ratio, which is a very important parameter, and signal to noise ratio is a measure that compares the desired signal level to the noise level. In a more precise way, it is defined as the ratio of the signal power to the noise power, and it is often expressed in decibels, dBs for short. So if you have a ratio which is higher than 1, it indicates you have more signal to noise, and if you have a ratio which is between 1 and 0, that indicates you have less signal than noise. So that means you have more noise than signal. So to increase, of course, your signal level, we need to have a large value for our SNR. So that means we are actually heading to have a SNR which is large. And in dBs, that means you need a value which is larger than 0 dBs. And if you have a smaller value than 0 dB, which is a negative, that means you have more noise than signal. Now, for this circuit, the SNR at the output for a specific frequency can be calculated using this formula. Already you have then the value in dBs, and since we already have the output referred RMS noise voltage, if you now substitute the values, we will have approximately 93 dBs. So it is close to 92.8 dBs. And we will verify this also, of course, in the simulations. So let's then look at the simulation results. First, we just start with the frequency response, and specifically we'll look at the bandwidth and also other parameters. Now, we see already in this plot, this is the circuit we have used, and we have the DC gain, which is approximately 26 dBs, and we have the cutoff frequency, and we have some labels to check our assumptions. So the DC gain is 26 approximately, and if you now convert this DC gain in dBs as a unit to a scalar value using this formula, you will have very close to 20. And that's exactly what our signal gain is. So that is a confirmation that the DC gain is correct. The cutoff frequency we have calculated using the pole frequency P1, 1 over that 2 pi RC, which is this external part. And if you again calculate it out using the 4000 and the 1 nanofarads for the capacitor and the resistance, we have then approximately 40 kilohertz and a little bit closer than 39.79 kilohertz. And if I look at my simulation, it is 39.73 kilohertz, which is really close to what we have calculated. What you also see, it's really important that we have some labels. But before we move on to that one, I will just make also the comparison here. So we have the parameter DC gain and the cutoff frequency calculation and the simulation next to each other. You can see the calculation and for the DC gain, also the simulation do match very well, and are exactly actually in this case. But there's the simulation is a little bit smaller for the cutoff frequency. That is of course due to our assumption that the complete dynamics of this system will be determined by this RC external low pass filter. But in any case, this is a very good result because the error is here very small. But we of course have assumed that the system was a first order system. And how can we check that? Well, for that, of course, first order system low pass, I need a slope here of minus 20 dB per decade. We need to check that. Let's check that, for example, by looking at this label. At 10 megahertz, I have a gain of approximately minus 43 dBs. It's a little bit smaller, so more negative. But if I go with my frequency 10 times larger, so 1 decade up, so to 100 megahertz, I need actually a decrease of 20 dB. So what do I see? I see here, if I go down, I see here the decrease is minus 40 dB. So it is actually a second order system, another third order system. So that is actually due to the part because this is the actual cutoff frequency, and the other cutoff frequency, what is actually due to this op-amp, is at the 900 kilohertz, which is actually approximately here. So then the system, it will behave as a second order system. So by looking at the later labels, your system is already second order. But if you look at the first part, which is actually this part, if you could zoom in here, that part is still behaving as a first order system. But then after the second pole, which is then at 900 kilohertz, the system will behave as a second order system. So if you look very closely to these two labels, which is given in red here, and that these are still around the first order part, you will see it is 17 dBs at 100 kilohertz. If I go 1 dB up, which is then 1 megahertz, I will have approximately, not exactly, approximately a decrease of decrease of 20 dBs. So it is of course not exactly, because I already make a transition from the first order part to the second order part, but you can see that it is a different slope here than there. You can also see that for yourself by looking at this slope, which is less steep than this one. So that is also a confirmation that the first part is the first order part, and the second part, due to that op-amp, will then make this complete circuit the second order part. But still, our simulations for the cutoff frequency is correct. But of course, we need to check the noise performance also. So let's look at the input noise voltage spectral density. What we see is the first part here, which is frequency dependent, because it is changing as the frequency. We also have a very large frequency band that will stay constant and independent of the frequency. So we have the first part, which is the dependent part, 1 over f noise part, and then also the independent part, which is then the broadband or the white noise part. We also have that part, which is here shown here, which is actually increasing without a limit for very large frequencies, but that will not be a problem in this case, because our circuit will filter actually out the frequencies above 40 kilohertz approximately in signal bandwidth, so that will be of course not the case. If I now look at the output noise spectral density, that is of course the multiplied version of the input noise spectral density, you can see again the 1 over f noise part, the broadband part, which is then just constant, and then you have then, which is approaching that part, after that part, approaching the zero value. That means actually the following. The first part is the frequency dependent part, 1 over f noise. The second part here, which is the constant part, is the frequency independent part. That is the broadband or the white noise part. And the other one is the output noise, which goes to zero. This is due to the band limiting of the op-amp and also, of course, the external RC low pass filter. So that's why we have the output spectral density will approach zero, and which is not the case for the input. Now let's also look at the total RMS output noise voltage, which is also, of course, one of the important results. This is the plot we have. Again, our circuit with our external circuit RC, and it starts off very small and then goes up and then approaches actually a very constant value for larger frequencies. So it is actually integrated up to 1 gigahertz, and I have here approximately 22.4 microvolts at 1 gigahertz. But our calculations were resulted in 22.8 microvolts RMS, and the simulation is 22.4 microvolts RMS. So this is a very nice result. These results here for the simulation and also calculation do confirm actually very well. So the error is again very small. And the final one is the signal to noise ratio, the SNR. Again, we can see it starts very large for the low frequencies and then drops very rapidly and then has some constant slope in the log scale, and then it approaches then a constant value for higher frequencies. So our calculation of the SNR was given by this formula, and we have used, of course, our output referred RMS noise voltage, and then have calculated using that value, and it was 92.8 dBs. And if I look at the simulation here, it is 93.0 dBs, and if we look also at the lowest label here, it is 93.01 dBs, though this is also a very nice result. So if you compare the simulation and the calculations, they also have very minimum error. So those are the results from the simulation. So we have actually done all the necessary calculations and also checked that in the simulations, and these were the results for the signal noise ratio as the final one. We have looked at the bandwidth. We also look at carefully the first order part and the second order part in our bandwidth to determine what the actual effect is of that op-amp and also the external RC filter. Okay, let's now jump to the SPICE simulation also to briefly discuss how we can generate these plots, and then we will end this example. So let's now look at our SPICE simulation. So we are now here at the SPICE simulation. This is our op-amp with the noise sources, noise input noise voltage source, input noise current source, the two resistors R1 and R2, and the external low pass filter, and this is our AC input voltage. So we have also, of course, the power the op-amp to have it operated, so we have the output here labeled. So we need to, of course, do the noise analysis. That's actually what we are interested in. And you can see it says the starting point of the frequency, it's then, let's say, 0.1 hertz, 1 gigahertz here. I just selected the lower and upper frequencies. These are the number of points to have an accurate plot. So these are actually what you what you can select at max in this simulation program. You have several plots, also diagrams. You can have the output noise, which is then output noise spectral density. You can have the input noise spectral density. You can have a total RMS noise voltage, because of course what we want, and also the signal noise ratio. So let's do all of them and then run this, and we will generate these 4 plots. To have also the body plot for the gain, we need to have a separate simulation. But let's first do the noise. So this is the plot. You can see the first one is the output noise spectral density. You can see we have the first part, which is the 1/f noise part, and it's then broadband, and then it approaches to, of course, 0 due to that bandwidth limiting of the op-amp and also the external RC circuit. Now let's also look at the input part. Again, this is approaching large values for high frequencies. If I, of course, make this more visible by looking at more ticks in the frequency axis, you can see it has, in this case, the 1/f noise part and the broadband noise, and also the part which is increasing without a limit. So then the total RMS noise voltage at the output, again, it starts off very small. So if I label this, let's say at 0.1 hertz, it's actually very small, with 0, and then it approaches and then goes to all the way to almost 22.4 microvolts in RMS. That's actually what you have integrated. Of course, you can go up to larger values for the frequency, but it will stay approximately the same. Okay, that's for the output RMS noise voltage, and also the signal to noise ratio is shown here. Again, it starts already large for very small frequencies, and then goes to a lower value if you increase frequency, and then it settles down at approximately 93.01 dBs, and we had calculated 92.8 dB, so this is also again a very nice result, and it confirms our calculations. So again, you have seen now also in the simulation how we can generate these plots, and I also discussed the calculation step by step, and also use the simulations plots to discuss what our calculations were and our simulation results. And we have seen that the results do match very well. Alright, this is our example number 4, and we have now actually discussed all of the topics and also compared again the calculation and the simulations. Thanks again for your attention, and if you have any questions, comments, please let me know. I will try to answer them as soon as possible. And don't forget to like and share this video so that we can reach more people for this very interesting topic. Good luck and have a nice day, and take care.